Lo sé, questo qui si me lo sé, si qua. Gracias. Parece que esto funciona.
¿Hay que usar esto?
Sí, sí. ¿Tienes frío? ¿Entra por algún sitio? Bueno, sí, yo...
Sí.
Esto...
Hola.
Aquí. No, ahí se va a mover. Mejor en castellano.
Hola.
Ok.
Oh, si no, no veo
So
alguna.
let's start. After all these technical issues, it's a pleasure to introduce Celia Anteniodo. She's a professor at the Pontifical University of Rio de Janeiro. And when you go into her webpage, you can see that she has worked on many, many topics. I would just say stochastic dynamics, non-equilibrium statistical physics, application of time series analysis, emergent collective phenomena in social and biological systems, sociophysics, population dynamics, dynamic systems, chaos, synchronizations, dynamics and thermodynamics of systems with long-range interactions. We still do that?
Along
Okay.
the history.
Okay. And probably other things that she had not. You have not updated your work page, probably. You have doing other things like aging. You know.
Yes.
Okay, she got her degree from the Brazilian Center for Physics Research, but she also did a stage at the University of Waterloo in Canada. And then she was a postdoctoral at the Biophysics Institute of the Federal University of Rio de Janeiro. And she's been a regular visitor of IFISC. I think this is the third or fourth seminar that she was here, and always on a different topic. So it's always welcome to this seminar.
Thank you very much to all of you. So I'm going to present work that is part of a project, as you see, with Eli, David, and also Luciano from the Bar-Ilan University. And I will give first not an outline, but an abstract, a graphical abstract that summarizes what this is about. What we have here are particles that we can consider as Brownian particles that are subject to a potential that is depicted here that has a well, but is flat at long distances. It's asymptotically flat. No? This is why we call it a non-confining. Far away, it is non-confining potential, which is a usual situation. And of course, if we try to calculate the usual Boltzmann partition function, it will be divergent due to this condition of flatness of the potential. But the Boltzmann factor plays an important role in this system, as we will see. So the question is, does this kind of system equilibrate? What? Ah, it's gone. Oh. Okay. The question is if this kind of system can equilibrate or not, apparently not. And but what we see when we look at the time behavior of dynamical or thermodynamical quantities, for instance, in this case, it is illustrated by the mean square displacement, but we can also consider thermodynamical quantities, energy, entropy, free energy. And what we see is what is illustrated in this plot as a function of time. There is a region that can be of long duration where there is a stagnation of the observable. So this is what we call a quasi-equilibrium state. And actually, it is named non-normalizable due to this condition of the partition function. So the answer to the question is that there is not a proper equilibrium, but there is a quasi-equilibrium state that we will see have some characteristics of equilibrium. And besides that, what we see is that the Boltzmann factor does not work. But if we regularize, what is that? It's me? It's other people participating. Ah. Hola. Well, so we will see that we can regularize in a way the partition function so that we can derive the thermodynamics in the usual way. Well, these are some of the works related to this part I will going to present. So this is really the outline. I will show a bit the motivation to study this problem, and then the approach to Langevin and Fokker-Planck equations, how we perform the regularization, and then another perspectives, another points of view to understand the problem. And let's pass quickly to the part of motivation. Well, as you know, potentials with this flatness are common from Coulombian gravitational, also interparticle interactions become flat at long distances. Here we are thinking not interaction potential, but in particles subject to an external potential. But this meant maybe derived from these particle-particle interactions. What we see is some substrate, maybe a biological membrane, a micelle, and particles around which are diffusing and can feel attracted to some region near the substrate, but this influence will become zero at long distances. And another situation we have in mind is, for instance, the case of optical traps, where particles are also diffusing, and there is some kind of traps, twister, something that maintains the particle confined in certain region, but this influence, of course, will vanish at long distances. So these are the situations here. I will not enter in the details because also I don't know all the details, but are some examples where this kind of effective potential applies and where also it is observed directly or indirectly the kind of stagnation I described before. These are kinds of, there are micellar solutions, also in the substrates that are nanotubes and well, other systems, many other systems. So the description is through, first we consider particles in the overdamped regime, Brownian particles. Then the description is through this kind of Langevin equation where the noise is zero mean Gaussian, and this force is derived from a kind of a potential of the type we are considering. Here is a paradigmatic example where we generalize the inverse Lorentzian function to reproduce a potential that has a well, but becomes zero at long distances. This is the associated force. So then we, here I show another case. The theory I will show is not restricted to this particular form that I will use as example, but there are other shapes, for instance, that illustrated here that may be very near minima, and also we can have some kind of barrier around the potential, and the theory also works for that cases. This is the simplest one. And then we use the associated Fokker-Planck equation to treat analytically the problem. And well, this is the usual form of the Fokker-Planck equation. What you do is we scale all the variables so that we arrive to this colored equation where we have just one parameter that is defined here is the relative temperature. Is the temperature relative to the depth of the potential well. We have actually another parameter that is this, which characterizes the decay of the potential, because we want to see how this decay affects the results. And here is the result of the numerical integration of the Fokker-Planck equation. and then we compute the mean square displacement a long time. You see here what varies from one curve to the other is the scaled temperature. At high temperature, we will tend to have something like free motion, because at high temperatures, the profile will become irrelevant. So we will have in this plot what corresponds to a straight line. And when the relative temperature decreases, we see that it starts to have some shape that gives rise to what we call a stagnation region, a plateau. For sufficiently low temperature, this emerges, and as the relative temperature decreases, this can become longer and longer. So it will be the trapping time, the problems I described. Our purpose is to describe the level that will define this level, will define the region of confinement, and also the time scales that will have to do with the duration we can expect the particles to get trapped in average. So this is what we see. And well, how to describe? If we try to find the stationary solution, we can solve this equation, and we arrive to a solution that is the Boltzmann factor, but of course is not normalizable. So what we have is summarized here. Is the following. Our initial condition is with a particle confined, not necessarily a Dirac delta, but they are more or less confined in the bottom of the well. And at very early times, what will happen is that these particles will diffuse, will expand in the bottom of the well. So at the very beginning, what we have is a diffusive motion. At very long times, most of the particles would have escaped, and again, we have the free motion. But it is in this intermediate scale when the region, the time window that is interesting for us, and where the almost or quasi-stationary state can emerge. What we have in this region, I am showing plots only in the intermediate time scale region. Here we have the dashed line corresponds to the Boltzmann factor. So we see that at the beginning it's not represented here. We will have some spread of the density distribution, but in the intermediate regime, what we see is that the central part of the distribution remains essentially the same, and what changes are the tails that start spreading diffusively. But since they don't have a significant contribution, we see this part stationary. So this is what will give rise to the stagnation part. So we have essentially two regions. One that is the central region, that is practically time independent, and then the tails that are moving diffusively, spreading diffusively. So this intermediate time scale will, the region of our interest is when or while these tails are not significant compared to the central region. We see that here there are several orders. Well, this is the essence of the problem. But, well, how to treat it? Here we see that as it's a reproduction of the previous figure, where in the central region, that is for a small x, around the potential well, we have the dominating the Boltzmann factor. All this related always to the intermediate time scales. I'm forgetting the beginning and the end. And then for large x at large distances, what we have is a diffusion solution. So we have an air-free function. This is because we don't have a delta initially. We have some spread, and this is the solution convoluted with the Gaussian solution after the initial spread of particles. So we have these regimes, and we also take into account that this form far away will be almost one, will become one, because the potential vanishes, and at large x, this RFE function will be almost unit. So we can match both solutions, because when one holds, the other is unit. So we propose, this is heuristic, but I will show a way to show this more rigorously. We can match both solutions and propose that the probability density function is given just by the product of these two factors, okay? The Boltzmann factor, that is time independent, and the complementary RFE function that depends on time corresponding to the spread of the tails. Okay, please ask me if there is something that is not clear. So we, okay, this is central. The fact for this to work is that the RFE is one near the origin, and this is one where the RFE function works. So I just will comment, will not show the calculations, but we can also use more rigorous treatment using, for instance, finding the solution by eigenfunction expansions, that it is what we have done in one of the works. And we can, considering always the intermediate time scales, we arrive at this form. Actually, there is a shift. There are some details I will escape here. Here, there are some that which are relevant. We have essentially two regions, the short X region, where we have the Boltzmann factor and another factor which gives a correction in time. And the part 3 is the part of the tails. We have part 1, part 3, and they match very well. The region 2 is not shown here. It's more complicated, but also it's not very relevant because it's a straight region, a narrow region that corresponds to region 2. 1 and 3 match almost well. You see that there is a shift. There are some corrections to the simplest expression that we obtained at first heuristically. And also I keep there the time dependence, because this will give the information about the time of duration, the time where we can consider the central part essentially constant in time. Is this expression is much smaller than 1, then we can obtain the time scales for which the quasi-stationary regime holds. Okay? Sí. Yes. The long time limit solution, most particles will have escaped, and you will have a spread like in normal diffusion, free diffusion. Well, no, because in the measure that particles start to escape and go far away, they will not have more information about the well. This regime is not interesting for us. It's this part where all these curves for any temperature. No. P of x in that regime. C, yes, yes. Will become flat, yes. Like if you had free diffusion, particles that are far away far away will not fill. Yes, most particles, after long times, most particles will be far from the well, from one side or the other. Okay, so no, well, equal probability, no, it will tend at very long times that there is not a normalizable solution. You will have all, it's like in equivalent to the case of free spread, which is the final state. We will have, yes.
You will have a Gaussian center of initial condition, while it's still it's a Gaussian center.
Yes. Yes, yes, yes. Mm-hmm. Mm-hmm.
Given by E minus B, which with spreads over infinity.
Mm-hmm. Yes, but well, we are interested in the quasi-stationary regime. Okay. Well, here at long times and large x, there are other details that I don't even remember quite well now. But you see that you don't see because the color is yellow, so we cannot see. But the red curve follows a straight line, like in free diffusion. And here the curves have another slope. The slope here is larger than 1. X squared goes, I think, as t power 3.5, and only for very, very long times it will reach the condition of normal spread. Okay. So there are some details, but we are not interested in this region beyond the, sorry, there is some insect here. Okay. See, I prefer the mouse. Okay, there are some details I will not enter here. Okay, only this slope is larger than 1. At very large times, it will reach the 1 slope, but not at this as soon as it leaves the stagnation, the plateau. Well. The solution, sí. The solution at the yes. Mm-hmm. Yes, so we make a lot of approximations. We don't use that expansion directly. We use no. The expansion solution is not exact. But it provides the first corrections. It's an expansion, actually. And we get the dominant terms, which allows us to get this. I have just one factor, one term here, but we have more terms of this expansion solution. I illustratively put only the first correction. Well, so the regularization, I will show which it is based. We start by this product of the two contributions, and to make the integration, again, we take into account the fact that there is some crossover point where this will start to take the value close to 1, and in the first region, this is close to 1. So we separate the integral up to this crossover point L in these two terms, okay? Here, a 1 is missing associated to F. Here, a 1 is missing associated to the Boltzmann factor. And then what we do is to reorganize terms. I will not show the details, to transform these integrations from 0 to infinity. So we complete the integrals and reorganize terms. And what we arrive at is an integral from 0 to infinity. Here there is a factor 2 because the potential in one dimension is symmetric. And there is another term, which is the F, which is the time-dependent term, and another one, which is time-independent, as this first, but it is much smaller because this is in the region beyond the crossover where this is almost 1. So it's negligible compared to the first, with this order exponential 1 over c, which is small. Okay, this is the dominant term. So we arrive to this expression where up to order square t, the constant of normalization is a constant, time independent. So this is what is our regularized partition function, which in this case consists simply in subtracting 1 from this exponential factor. It is normalizable, which is valid, here it is written, when the potential decays faster than 1 over x. If the potential decays more slowly, then we will have to subtract more terms to turn the integral finite. And well, here we can resolve exactly. I just put the order, but this will allow us to compare both terms and extract the time scale where this approximation holds, which is associated to the duration of the plateau. So this is the idea. This is the simplest case where we just subtract one term. So we have this time-independent part that will be our regularized partition function. Here is a plot where this is the complete integration, and it is separated in the first part is this gray region. And we see that this part contributes, is negligible against the region, the central region. And this is the time dependent term that here is exaggerated. But when this term becomes small compared to the first, we will have the quasi-stationary regime. Okay? Okay, so for other potentials, we will have to make a different correction. Here I am showing the case of the square, the mean square displacement. As we have here a factor x squared inside the integration, this will make more difficult the convergence of the integral. So for the case I have shown before, where the decay is as 1 over x, we will have to subtract more terms. So I have written here the simplest expression, but it only holds for potentials that decay as 1 over x3. Okay, so this is the calculation of the mean square displacement, and here is shown the calculation is shown by these dashed lines against the results of the numerical integration. Okay.
Say that the previous expression, the normalization, was how the new previous
one. Here, mu has to be greater than 1. Okay, but if I'm calculating this integration to regularize it in the case used before, it's not enough to subtract one term. I will have to subtract more terms. I will show it, but just to put a full expression. But this is valid in the case where the decay is a bit faster, as 1x power 3, okay? So this is the full expression in that case that matches as soon as the temperature is small enough and the stagnation region is well defined, it describes precisely the level. Here is the case where the full expression for the terms we have to subtract. This number of terms will depend on the potential shape and also on the observable we are integrating. For instance, for the partition function, a certain number of terms will be enough, but if we have some observable that is a power of x, then it will complicate the conversions and we'll have to subtract more terms. Eh?
This is an exponential.
Exponential.
Look up here is the first step of an exponential expansion.
Yes. These are the terms of this exponential expansion, exactly.
Like replacing the exponential expansion by
like making a truncation of, yes, exactly. And here I'm showing the full expression that I didn't want to show it at first. In the case when the potential is 1 over x, then we will have to subtract more one term for the partition function, because the first expression was only valid for faster than 1 over x. And in the case of the numerator, we have to subtract this number of terms. Okay, and this is in the case of 1 over x, the comparison with the exact results.
But it's not that you improve your result by including more terms.
No. It's a right regularization. If we don't include the terms, the integral will not be convergent. Yes.
You need to say how many terms you want.
Yes. We know. I have not written the expression here, but we have the expression that depends on the potential decay and also on the form of the observable.
But it's not that the more the better. It's not that the more terms you use, the better. Because if you
no. Well, here are the plots for the thermodynamical observables. And in this case, we see that because of the behavior of the observables, the convergence is easier. And this gives rise to longer stagnation time. So the characteristics of this quasi-equilibrium depends on the observable. Depending on the observable we're looking at, the duration will be different. The regularization in the numerator will be also different for each observable. But we have a rigorous expression to show the number of terms we need to subtract in each case. And here there are also some expressions that are still valid after the regularization, like this connection between the energy and the logarithm of the partition function. Also, this expression for the entropy are still valid after regularization, as in the normal equilibrium state. Another observation I wanted to add here is that a way we can see the problem. Here is the true potential, this violet curve, and this is the harmonic approximation. In that case, we can have a crude estimate using an harmonic approximation. For instance, in particular, for this potential, it may work. Not for a potential which have a lot of structure. The harmonic approximation will not be very precise. But what we can see is that the type of regularization we are using would be equivalent to using this effective potential. That is better than the harmonic approximation. In this part of the well, it reproduces well the true potential, and far away, it is confining. So it solves the problem of the non-integrability. Here, perhaps, is rather a mess. These are the exact results, the curves from the numerical integration. And here, these lines, this short dash are our calculation, which corresponds to the theoretical course. These dotted lines are the harmonic approximation that you see that is not precise. And even worse for the other kind of potentials, as the first I have shown to you with many mean. So this is another view. What this regularization is doing is to use an effective potential of this type. Of course, another observation I must do is the regularization is not unique. We can, in the same way that if our regularization corresponds to this green dashed line, one can imagine other approximations for the potential, and then this will give rise to other regularization expressions. How much time there is? Over? Okay. So just I wanted to comment another perspective, another form to address the problem is to avoid the non-integrability at those distances is to consider our original potential well, but to wall it, to put walls so that there will be a true equilibrium in that case, because the system is confined. And what we can do, depending on the time scale we're interested, we will move the wall so that the system will behave the same in the region of interest. In this case, as we have an exact expression, we have some advantages. At the end, we will have to regularize in the same way. Let me see here the behavior, as we have seen before. This is still the mu square displacement as a function of the temperature. In a case that is here, is the decay as quartic x. And here is the corresponding plot as a function of L. You see that there is some correspondence between them. So the same problems will arise. We just are translated the time in the length scale. We have a partition function that we can calculate the equivalent integral of the partition function. But if we want to do L tending to infinity as our original problem, then the same problem of convergence of integrals will arise, and we have to perform the same type of regularization. We arrive to the same expressions. Well, this is the equivalent to what I have shown before. Well, the same for energy and entropy. We have always, for these quantities, the plateaus long more. But an advantage of this perspective with the walled potential is that we have closed expressions. We can calculate, for instance, the inflection or the log inflection point to define a point where we calculate the square displacement, and we have then a closed expression for the mean square displacement. And well, we made the assumption that this log inflection point also corresponds to the value at the log inflection point correspond to the value at the inflection point in time, which is we have not a rigorous demonstration for that, but numerically it works. Here is I summarize the results for the square displacement as a function of the relative temperature, where you see this, the black line is the result of the numerical integration. This is the harmonic approximation that in this case, you see, doesn't work too bad. It's not so precise, but for this kind of potential, it's not too bad. For very small temperatures, it will work well. And here the other symbols corresponds to the result from the log inflation points. This dashed red line is simply a small x approximation for our theoretical curve. That works, even this approximation works better than the harmonic one. So we have also studied a variant for substituted normal by anomalous diffusion, where we substituted the time derivative by a fractional derivative, and we performed also the random walk simulation using continuous time random walks. The lengths of the shafts were adjusted to reproduce the potential and the waiting times according to the power law distribution. That is the time of walks corresponds to this operator. And well, we see good agreement. Also, our theory works well. This is the prediction of the regularized case. And in this case, we also studied the dependence of the duration with the exponent that characterizes the waiting time distribution. This was motivated because some of the experiments I mentioned at the beginning, especially those in biophysical systems, diffusion is anomalous. There is a subdiffusion. So we were interested because of this. And well, there are some details that are too technical. I will skip this. So we have shown that for this kind of flat potential, a possible treatment, we don't claim it's the only one, it's possible to regularize the usual partition function and use the normal tools of equilibrium, true equilibrium. We have rigorous results through the eigenfunction expansion, but for the first correction, it gives the results we obtained by the empirical, the first guess. So the purpose was, as we obtained the values, precise values of the level of stagnation, and also we can predict the duration, mainly the duration of the stagnation region. So as perspectives, there are other lines we are working. We have worked with this fractional dynamics extension, but there are other variants that fractional dynamics or other forms on anomalous diffusion we could include. We must still analyze the relaxation properties, fluctuation dissipation relation, especially relaxation properties. We have not studied yet. Also variance with, for instance, stochastic resetting. And this is more ambitious, is the problem of interacting particles. Here are particles subject to an external potential, but for interacting particles, so through Lennard-Jones or some kind of potential of this kind. Well, this is the main results I wanted to transmit to you today.
Okay, thank you. Any questions?
What you mean exactly? Well, we calculated, we observed that there is the stagnation, the duration is much longer, but that for the energy or even the mean square displacement, of course, because in that case it is shorter. Perhaps you mean if we studied the increase of entropy or no, we didn't. Because in this case, it's not the true stationary state. The system is permanently evolving. It's not in a stationary state. The region is flat, but there is a certain slope. The slope is small, but the system is always evolving.
Celia,
Sí.
Take a nonlinear Volter model
Huh.
in the regime in which the exponent is smaller than 1. You have a potential like the one that you have there, and precisely in a bounded domain, because the magnetization density is between -1 and 1. The difference there is that the walls here are absorbing states, and then you know how to calculate a quasi-stationary distribution, which would be the equivalent of what you are doing. Now, imagine you take this nonlinear Volter model in which you have this potential, which asymptotically is flat in a bounded domain, but you consider a noisy nonlinear Volter model so that you do not have any longer absorbing states. The question is, can you apply what you have done to calculate intermediate stationary distribution there? And how would that reflect the fact that there is a noise-induced transition?
Well, first, it's not any potential of that as that drawn over there. This regime where the theory is valid will be when the potential is deep enough. That there is a temperature that is small compared to the wells depths. So if I don't know in which case we may have a very steep potential. Well, if we had, because otherwise the approximation will not be valid. Really, I don't know. We have to think. But if we have analogous situation with the deep potential well compared to the temperature, perhaps we can. It's worth to think more about.
It was a suggestion.
Thank you.
You consider more than one well?
Well, yes, in this, for instance, I have not shown the results in the presentation, but we consider this kind of profile. And if you mean wells that are separated enough, the thing will be different. Here there are more or less localized. If you, the separation between the wells will be important.
I suppose the simple case of.
Yes, but if they are separated or not, if they are overlapped in some way, then we will have the same. But in the way they become separated, then I'm not sure, but perhaps we have more than one stagnation level.
Yes, because I guess there will be like an increasing time.
Yes, and can become trapped. Also, here we are starting from a particular initial condition. Nothing need to be strictly localized, but more or less around the region of the well. If we start with something outside, the behavior will be different.
Thanks.
I was having the same situation. It's when you have a double well, but I mean not flat, simple double well, the 5-4 potential. The minima, you start from one of them. for a long time, you will simply have a distribution centered around one of the wells. That will be a quasi-stationary distribution until at the very end, you have the two maxima, the two wells.
Yes.
But there is a long time, depending on the barrier, where you have basically a quasi-stationary distribution.
Yes.
Would that be
Yes, I
used to-
think it.
Would that be used?
Mm.
The potential is not flat. Okay.
Not even if it's not flat.
Okay.
Yes.
I would be very much interested in.
Yeah, because here actually it is flat, but if it were not, and we have done the case, I don't know if it is here, where we considered barriers like here. No?
Okay.
We have these barriers, and the theory I was in that it was yesterday thinking in the and it works. No? So if I have and also another answer, it's not the speculation, but another concrete answer is this effective potential. I cannot find this. I have shown to you an effective potential.
Yeah, okay.
So
Yeah, well,
it is not flat because it increases more slowly. I don't know if slowly.
We need to talk more
Yes,
about this.
so,
Sarah will be very much interested into this. Okay. Any other questions from the online participants? Okay. If not, we'll thank Theli will be here until Friday. Okay, want to talk to her, and she will be going next week to the Complex System Spanish chapter of the Complex System Society meeting also. Okay. Thank you.
Eh?